In this video, we are going to be doing curve sketching, and it's really interesting because we're going to be learning how to look at a function and analyze just by looking at it some things that are going on, and then finding certain things like the y-intercept using the first and the second derivative along with the critical numbers and inflection numbers to get some points and to graph this. And we'll see that when we follow getting certain information sequentially, that the graph will just build itself, and it's really cool. All right, so the first thing that we are going to be looking at here is finding our y-intercepts. Well, to find our y-intercepts, all we do is set our x equal to 0. So that's going to be 0 cubed plus 6 0 squared minus 15 times 0 minus 1. So our y-intercept is 0, negative 1. Okay, and then we need to find our first derivative. Well, the derivative of x cubed, we have 3x squared plus 12x minus 15. Then we need to find our critical numbers. Well, what are our critical numbers? Our critical numbers are found when our first derivative equals 0. So let's go ahead and do that. And we will set our first derivative equal to 0. Which I probably should give myself more room, because in order to set this equal to 0, we're going to use the quadratic formula. So if you don't remember, which I hope you do, the quadratic formula, we'll go through it real quick. All right, so we have negative b plus or minus the square root of b squared minus 4ac all over 2 times a, which is 6. So we'll just write 6 right here. Okay, so 12 squared is 144, I think, minus, I'm going to need a calculator. Okay, so negative 4 times 3 is 12, times negative 15 is 180, positive 180, because we have a negative times a negative. And so 144 plus 180 is 324. So we have the square root of 324. Just trying to make it to where I have some room here. So then we're going to have negative 12 plus or minus the square root of 324, which is awesomely 18, a perfect 18, over 6, which is going to be negative 12 plus or minus 18 over 6. So it's easier, I think, to break this into two equations. We're going to have negative 12 over 6, which is going to be just negative 2, plus or minus 18 divided by 6 is 3. So that means we have two critical numbers because we have this plus or minus. And so it's going to be negative 2 plus 3, which is going to be 1. And then we also have a critical number at negative 2 minus 3, which is negative 5. So we have a critical number at x equals 1 and x equals negative 5. All right. So now let's take our second derivative. So our second derivative is the derivative of the first derivative. So here we go. We have 6x plus 12. And then we need to find our inflection numbers, and let's go over real quick what the critical numbers are. So critical numbers are changes in direction of your graph. So you're going to have some change in direction, x equals 1 and negative 5, either changing, increasing, or changing to decreasing. Well, inflection numbers tell us about the concavity of our graph, meaning am I frowning or am I smiling? And we'll see what that looks like when we get to the number line and then when we graph this. But what we'll do is we'll go ahead and take the second derivative and set it equal to 0. So that becomes, we can just leave it like that. And so then you'll have, move this over. minus 12, 6x, divide by 6, divide by 6. So x equals -2 is our inflection numbers. All right. Oh, well, I guess I can put those down here. Okay, and then we want to know our critical points. Well, right here we have critical numbers, but in order for it to be a point, we have to have a corresponding y value. And how you get that is you plug these numbers back into the original function up here. So let's do that. So we have, and you know what, instead of I'm going to use synthetic division to do this because I think it's just easier than plugging everything in. Now for 1, it's easy to just plug 1 in, right? We'll have 1 cubed plus 6 times 1 squared minus 15 times 1 minus 1. So we're just adding them together. We have 1 plus 6 minus 15 minus 1. So this is minus 16, and this is a plus 7. So we have a negative 11 for our 1. So we have a point at 1, negative 11. And then we have for negative 5, we're going to do synthetic division to find our y. This is pretty cool, I think, to do it this way. So you take your negative 5 and you put it right here in a little box. And then you're going to write your coefficients. Now they have to have all of the powers represented. You have to have like 3, 2, 1, and a constant. So say this went from 3 to 1, I would have to put a 0 in the second power place because everyone has to be represented. So we can say 1 plus 6, we have minus 15 and a minus 1. Then I'm going to leave myself some room to work, and I'm going to bring this 1 down. And then I'm just going to multiply and add, multiply and add. So negative 5 times 1 is negative 5. 6 plus negative 5 is 1. Negative 5 times 1 is negative 5. Negative 5 plus negative 15 is negative 20. Negative 5 times negative 20 is positive 100. Negative 1 plus 100 is 99. And this 99 is our y value for this negative 5. Isn't that cool to do it that way instead of just like plugging everything in and like accidentally messing something up? But you could if you want. If you really want to plug everything in, you can. But I thought it'd be cool to show that. Negative 5, 99. So we have 2 critical points. So like I said, these are going to be where our graph is changing direction, either going like this or like this. Okay, now our inflection points, well, it's the same thing. We have right here an inflection number, but in order for this to be a point, we need a corresponding y value. So we're going to plug this inflection number into our original function. And I'm going to do synthetic division again. So we have negative 2, and then we have 1, 6, negative 15, negative 1. We bring the 1 down. Negative 2 times 1 is negative 2. 6 plus negative 2 is 4. Negative 2 times 4 is negative 8. Negative 15 minus 8 is negative 23. Negative 2 times negative 23 is a positive 46. And then we have negative 1 plus 46 is going to be 45. 45 is my corresponding y value for this inflection point. And our inflection point is where we're going to have a change in concavity. So something like, if you see this, well, if we look really close right here, something happens right about here. And we go from frowning to smiling. This is that inflection point. So now we don't know if it's going to be going from frowning to smiling or from smiling to frowning yet, but we do know that we're going to have this change in curvature of our graph. Okay, so the next part that we're going to do is we're going to draw a number line to show where f of x is increasing or decreasing, concave up or concave down. So we're going to put all of this together. All right, so in order to do our number line, we're going to need our critical numbers. Whoops, this thing's moving. And we're going to need our inflection numbers. All right, so here we go. All right, so we have a critical number at, I'm going to do a different color. We have a critical number at x equals -5 and at 1. These are our critical numbers. We have an inflection number at -2. Now what we need to do is we need to pick some test values. Test values are just numbers that come in between these intervals. So anything below -5, I'm going to choose -100. So this will be a test value. And then between -5 and -2, well, we could do -3. And then between -2 and 1, well, we have 0. 0 is always nice to plug in. And then 1, I'm going to do over here, anything above 1, I'm going to do +100. Now, what we're going to do is we're going to plug all of these. We'll start with our test values, and we're going to use the first derivative. We're going to plug all of these test values into the first derivative to see where our graph is increasing or decreasing on that interval. All right, so our first derivative was, let's write this down, f prime of x equals 3x squared plus 12x minus 15. All right, now we will have to, I'm going to erase this so we have some room to work. All right, we're going to plug in first and foremost this -100, if I can get my pencil back. Okay. So f prime of -100, all we want to know is the sign, whether it's positive or negative. And that'll tell us if it's negative, it'll be decreasing, and if it's positive, it'll be increasing. Okay, so if we have this is going to be a really big positive number minus a really big, well, that's more than 100. It's going to be lots of zeros. I don't even know how many zeros off the top of my head. Let's see. -100 squared is 1, 2, 3, 4 zeros. So one more zero. So we have that times 3. It's like 30,000 minus 1,200. Okay, so this is going to be a positive number. So since it's positive, we are increasing on the interval -infinity to -5. Because this -100 is representative of all the numbers that would come before -5. So we have that we are increasing, actually I'm going to do it in blue because we're using the first derivative, and this is about critical numbers changing direction at critical numbers. And so we're going to plug this into the first derivative, and we got that it's increasing. Well, now we're going to plug -3 into the first derivative and see what's happening there. So we have 3 times -3 squared, which is going to be a positive, plus 12 times -3 minus 15. So we see here that this is going to be 27 plus -36 minus 15. This is going to be a negative. We don't care what the value is. We just know that it's negative, and therefore it's decreasing on the interval -5 to -2. Now, let me do it in blue. Do you see how we change direction at a critical value? Well, let's see. We're still going to plug in this next test value. We're going to plug this into the first derivative, and we'll see what happens. But now we're crossing an inflection point. So we'll see what happens at an inflection point as far as increasing or decreasing. So we have f prime of 0 equals 3 times 0 squared plus 12 times 0 minus 15. And we get a negative answer, which means we are still decreasing. But now we're decreasing from -2 to 1. So why didn't we change direction there? Well, because this was an inflection number. And what changes at an inflection number is our concavity, the personality of our graph. Are we positive or are we negative? That's what's happening. But we're not changing direction. Okay, so then we have our last test value. This is going to be f prime of 100. We have 3 times 100 squared, which we now know is 10,000, plus 12 times 100 minus 15. So this is going to be a really big positive number. So it's positive, and therefore we are increasing on the interval 1 to infinity. Now you see we changed direction again, and that's because we we passed a critical number. And so let's see now what happens. Now remember, to find our increasing and decreasing, we plug that into the first derivative. To find our change in concavity, we're going to plug these test values into the second derivative. All right, so let's do that. So we have our second derivative was 6x plus 12. All right, so let's do f prime prime of x was 6x plus 12. So we're going to have f prime prime of -100 equals 6 times -100 plus 12. So this is a really big negative number, and that means that we are concave down. We are frowning from -infinity to -5. So what does that look like? Well, we are concave down. So we'll put that on our number line, and it'll make more sense when we start to put everything together. All right, so then we have our test value of -3. 6 times -3 plus 12 equals, this is going to be what, -18? So we have decreasing because it's negative. So we are decreasing from -5. Oh, hold on, sorry. I shouldn't say decreasing. I should say concave down. Concave down from -5 to -2. Oops. All right, so what does that look like? Well, you see, we were still concave down. Now, if we take a look at this here, if you are you're increasing and then you're decreasing, you have to be concave down, because going up, you see here, this is a maximum. So if we were to put these two together, you would see that we have a max, right? We have on our graph a point that's like that, right? Which would be the top of a point. So if I'm going up and then I change direction, it would have to be concave down both ways, right? Okay. So now let's do our next one. So we have f prime prime of 0 equals 6 times 0 plus 12. Well, now we are positive, so therefore we are concave up. We're smiling on the interval -2 to 1. So we changed concavity here. We went from, let me redo that. We went from frowning to smiling. And you see that happened at an inflection point. All right, so let's see. Now here we know that it's just a critical number. So I will bet you that it'll just be, again, concave up, which would make sense because right here, if you look, we're gonna have a minimum. So instead of like over here, we were like this, now we have it to where we're down, right? All right, so let's see though, just to make sure. F prime prime of 100 equals 6 times 100 plus 12, which means positive, which means concave up on the interval 1 to infinity. All right, so if we look at these pieces on our number line, we can see that our graph is going to be, let me use a different color. Our graph is going to be increasing concave down, and then decreasing concave down, and then, let me see, increasing concave down, decreasing concave down, decreasing concave up, and then increasing concave up. So something like that is what it'll look like. Because if you see, if we take, see we have, let's see, right here, we have this going up. Well, you see that part right here. And then you have this part going down, so that'll be that part. And then we're going up, so it's going to be like this. Actually, it would be probably more. It's down. It'll be more like, if I can get my pen back, like that. So you see we have these changes in our graph. Hold on. We are, come on pen. I've been using this so much that I think it's tired or something. So we're increasing, decreasing, still decreasing, and then increasing. But we have that we are increasing concave down, decreasing concave down, still decreasing, but now we're concave up, and then we're still increasing concave up. You see that? All right, so we'll see it better when we, if you don't see it yet, that's fine. We'll go ahead and we'll graph this thing. All right, let me see if I can move this up. All right, so in order to graph this, we're gonna need our points, which we had as -1, -11. This was critical. And then we had -5. Oh, it wasn't -1. I just made that up. It's 1, -11. Then -5, 99. And then we have inflection points at -2, 45. And then we had a y-intercept at 0, -1. And then we could get x-intercept, but this function is not easily factorable, and this is not a factoring video, and we don't really need it to do this graph, so we're just not going to do x-intercepts. Okay, whoops. In fact, none of the graphs that we're going to do on here really need the x-intercepts. So if they're not easily found and you don't need them, you know, it's fine. All right, so we have our critical points, our inflection points, our y-intercept, and then now let's go ahead and graph this baby. So we have no vertical asymptotes because there was nowhere that this function was undefined. So we have a point. Let me go ahead and make some marks here. 1, 2, 3, 4, 6, 7, 8. Oh, my y is going to look crazy. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is, my graphs are never to scale, ever. So if I count by 10, I should be all right for my y. So these are values of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and I'm pushing it, 100. Okay, and then 1, oh, that'll be 10 and 22. Okay, so we have a point at 1, negative 11, which would be like right there, because remember that's a negative 11. 1, negative 11 would be like right there, because that's a 10. And then we have a negative 5, which is 1, 2, 3, 4, 5, 99, oof, which is going to be up here. I'm going to move these. I'm going to move these down here and erase these, so that way we have room to see what this beautiful graph is going to look like. Okay. All right, so we had the 1, negative 11. Now we have negative 2. Where's my pen? Come on. All right, so negative 2, 1, 2, and then we have 45. So this would be 10, 20, 30, 40, 10, 20, 30, 40. So 45 is like right here. And so we said negative 2, 45. All right, let's erase him. All right, and I'm going to make this guy a little bit bigger. Then we have negative 5, 99. So we have 1, 2, 3, 4, 5. And then we're going to go way up here to 1, 2, 3, 4, 5. Up pretty much all the way. And then a y-intercept at 0, negative 1. So it's going to be like right there. All right. So now when we go and we look at how our number line was, we know that we are increasing from negative infinity to 100. If we look here, you see that we're increasing from negative infinity to 100, but we're increasing concave up. Okay, so what does that look like? Well, we're going to go like this. Increasing, or excuse me, concave down. That didn't really. Okay, and then we see that we are decreasing, still concave down, and we're doing that until we get to the negative 2. So like this. Whoop. Moving my graph. All right. And then we have an inflection point. Remember, we have an inflection point right here at negative 2. And this is where we're going to change concavity. So we're still going to be decreasing. We're still going to be decreasing, but now we're going to be decreasing concave up. That's going to be like this. And then we have right here, you can see we're going to be increasing concave up. So then it'll be like this. And that is our beautiful curve. That's one thing I love about polynomials, is they are these smooth, beautiful curves. All right, there we go. And let's do another one. Okay, so we have a function that is f of x equals x divided by x squared minus 9. So the first thing we're going to do is we're going to find the vertical asymptotes. Well, the vertical asymptotes are where the the denominator, what would make that equal 0. So let's go ahead and do that. We'll set the denominator equal to 0, and we'll see that we have 9, we have x squared equals that, so that means x equals plus and minus the square root of 9, which is going to be plus and minus 3. So at x equals negative 3 and at x equals positive 3, we have these vertical asymptotes. They are lines that means that you can never ever touch. Do not touch ever. can't ever touch them. Okay, and then we have horizontal asymptotes. Let's find those. Oh, I should have gave myself more room. We'll see what happens. Okay. Well, here we go. So it's going to be the limit as x approaches infinity, that is an 8, not an infinity, of x over x squared minus 9. So we're going to multiply that times the highest power x on the bottom, or excuse me, divide each unit by the highest power x of the bottom. And remember, there's a theorem that says if we have a constant over a power, and this could be x to the first, or it could be x to the 50th. It doesn't matter. If you have a constant over a power, then your limit equals 0. And that's where this comes in. We divide everything by this x squared so we can apply this theorem. So this is going to go to 0. X squared over x squared will go to 1. And then we have the negative 9 over x squared will also go to 0. Okay, so let's do this. So we have this equals, oops, wrong one, equals the limit as x goes to infinity of 1 over x, because one of those x's will cancel, and then x squared over x squared is just going to equal 1 minus 9 over x squared. And then let me erase this here. Come on. Okay. Equals the limit as x approaches infinity of 0 over 1 minus 0. And remember, anytime we have 0 over 1, that is well defined, and so that just equals 0. So that means that we have a horizontal asymptote at y equals 0. Okay, let's see. There we go. Let's go ahead and do like this, so we know where our good stuff is. All right, and then the next thing that we're going to do is our y-intercept. Our y-intercept is when our x equals 0. So we have f of 0 equals 0 divided by 0 squared minus 9, which gives us a 0 over minus 9, which equals 0. So we have a y-intercept at 0, 0. Okay. Now we need to take our first derivative, and our first derivative, this is going to be a quotient rule derivative, so we're going to have the bottom squared over, we're going to put the bottom just how it is, and then we have the derivative of the top, which is just 1, minus the top just how he is, times the derivative of the bottom. Okay, and so that is going to simplify to x squared minus 9 minus 2x squared over x squared minus 9 squared. All right, and now you can't just cancel this guy right here from this. You can't just take him out because he's not factored out. He's still a part of what's going on. He's actually minus something, right? So we haven't pulled him out front, so you cannot cancel these two. All right. And so let's see, that's going to give us an x squared minus 2x squared is going to give us a minus x squared minus 9 over x squared minus 9 squared. All right. Well, now what we can do is we could pull out a negative just to make it easier for us to see. Now, when I take the second derivative, though, I'm going to use this part of the derivative, but when we're plugging in to get our critical numbers, I I'm going to use this one. I'll show you why in a second. X squared plus 9, if you pull out that negative, then you get x squared minus 9 squared. All right, so these two, either one of these we'll actually use both of them in different arenas. So we're going to use this one, though, to find our critical numbers. And that's because just doing the negatives is it's extra. And I think it's easier to see with this that our derivative will always be negative, which means that our derivative our function is always going to be decreasing, because the top is always going to be negative and the bottom is always going to be positive because it's going to be squared. So no matter what it is, it's going to be squared and it's going to be positive. And so I think that's just helpful to see that our graph will always be increasing. Or excuse me, will always be decreasing because it's negative. All right, so our critical numbers. Well, the only thing that could make this equal 0 is the top. So we will have, and I'm going to only do x squared plus 9 equals 0. And the reason I'm going to do that is because this is just like having a -1 out here, and that's just like having a multiplier, and you don't take the derivative of a multiplier, right? So it's just easier to do it this way, I think. Okay, so x squared equals, and we move that 9 over, and we see that you can't do that. This is an imaginary number. And the reason that we don't get any, so this means no critical numbers. Well, what is a critical number? A critical number is where the graph changes direction. But we just said that our graph is always decreasing. So we don't have any of these because we are always like this. Now, your concavity will change. You could be up or you could be down, and that'll change the look of things, but you're always decreasing. So no critical numbers. Good to know. All right, now we're going to take our second derivative, and I'm going to use this guy to take our second derivative. All right, so we have, this is a quotient rule again, so it's going to be the bottom, and it's this right here. This is what I'm taking the derivative of. This one, I'll circle it. Okay. X squared minus 9 squared, that's why we get the 2 times 2, which is a 4. And then we're going to write the bottom as he was, times the derivative of the top. Well, the derivative of negative x squared is negative 2x, minus the derivative of the bottom. Well, we have a chain rule derivative here. Oh, actually, let's do the top how he is. Negative x squared minus 9. There we go. To be consistent with how we did the other ones. And so we'll say x squared. So we have the 2, because we had to bring this guy down first, and then, so we're doing the derivative of the power first, and then we have the inside at how he was. He doesn't change. And then and so this would be 1, but we don't need to have that right there because a 1 goes without saying. And then we're going to have the derivative of that, which is 2x. Okay, so let's put this all together. Well, first things first, we know that when we have, if we start with, like up here, our original, where are we at? Oop. Our original function started with a power of 1 on the bottom. When we took the derivative, we went up to a power of 2. When we take the next derivative, it can only go up by a power of 1, so it'll go up to a power of 3. So when we're looking at this right here, we see that right now we're at a power of 4. But we know that that needs to be a 3. So we know that at some point, if we do everything correctly, that we're going to be able to factor out an x squared minus 9 so we can cancel one of these guys. Okay. So keeping that in mind, I'm looking around and I'm seeing that I have, let's go ahead and put some of these together. So we have negative 2x, x squared minus 9 squared, minus, and then I'm going to put these two together. So I'm going to end up with negative 4x. I'm going to bring him out front. Negative 4x. And then I'm going to, because he was connected to him, so I'm going to put him right here. We have x squared minus 9. And then I am going to bring this guy down right there. And this is all, it's just like addition. It's multiplication, so you can, as long as whoever's being multiplied, like I couldn't take him and put him over here because he's multiplying him, but we can switch, you know, it's still going to be the same answer. Okay, so now that we have this, well, let's go ahead and do that. All right, so now we see that we can take out a negative 2x, and we can also take out an x squared minus 9. You might have been able to see that up here, but I feel like it's more in your face right there. So let's go ahead and do that. Let's take out a negative 2x and an x squared minus 9. Okay, and so then I'm going to go down the line and see who's left. Well, I see that I still have one of these guys left, so I'm going to put him right there. So I have x squared minus 9 minus, and then I get right here, and I have a 4x. Well, I already had a negative 2x, so that means I just need to put in a 2. And it needs to be a plus 2. Because I took the negative out too, so you have to watch that. You have to watch your signs. We took the negative out as well, so this is going to be plus 2. And then we took this x squared minus 9. He's already represented for, so we leave him alone. And then we put this guy right there. It's going to be negative x squared minus 9. Okay. And now we are over x squared minus 9 to the 4th. But now we see that we can get rid of one of these. That becomes 3. Okay. So we have negative 2x times, and then we're going to put these together. We have x squared minus 9. Well, I see here that I have a minus, so I'm going to pull him out right there. And this is going to be, I'm just going to distribute that 2, minus 2x squared minus 18. And then I have x squared minus 9 to the 3rd right there. Okay, so now we have a negative x squared, or excuse me, a positive x squared and a negative 2x squared. So this is going to give me a 1x squared. We still have our negative 2x. So we have negative x squared, and then minus 9 minus 18 is minus 27. All over x squared minus 9 cubed. And this is your derivative. But if you see here, we have a negative here and negatives here. So I'm going to go ahead and I'm going to redistribute that negative. And I find that that happens a lot. So probably it's best to not take the negative out so you don't have to redistribute it at the end. But I just always find it so irresistible to take the negative out. So, you know, do what you must. So 2x, and that becomes x squared plus 27 over x squared minus 9 to the 3rd. Okay, so now we're going to work on our inflection numbers. Well, that involves our second derivative and where the second derivative equals 0. So this is our second derivative. And again, what can make the second derivative equal 0? Well, that is going to be anything that makes the numerator equal 0. Technically, it's also where the second derivative is undefined, but we've already accounted for the fact that we have, or it's also where the second derivative is undefined, excuse me. So this, though, is already accounted for in our vertical asymptotes where we said x equals plus and minus 3. So we don't need to be repetitive and put that again. Okay, so the only thing, well, let's put the whole thing, that will make 2x, x squared plus 27, 0 equals 0 when? Well, when 2x equals 0, or when x squared plus 27 equals 0. And so this is going to be negative 27, and then x squared. We have x equals plus and minus the square root of negative 27. This is imaginary, so that doesn't count. So this is not a critical number. And then over here, though, we have x equals 0, and this is a valid inflection point, or excuse me, inflection number. Okay. Now, our critical points and our inflection points. So just like we just found our inflection numbers, well, in order to have a point, you have to have a corresponding y value. So for our inflection, or excuse me, for our critical, we had no critical numbers. So because we have no critical numbers, we have no critical points. Okay, so no critical points. Well, what about our inflection points? Well, we have here that x equals 0 was an inflection number. So now we need to take our inflection number and plug it into our original function, which was, let's see right here. All right. Ooh, come on. Well, I think he just decided he was done moving. Maybe not. Okay. There we go. So I can see him. So we have f of 0, because we're plugging in that inflection number. So we have 0, 0 squared minus 9. Well, that's going to give us 0 over negative 9, which equals 0. So we have an inflection point at 0, 0. Okay. And then it says here to draw a number line to show where f of x is increasing or decreasing, concave up or concave down. So let's do that. We're going to have this number line. Now, remember we said that we had no critical numbers, but we do have some asymptotes. And we had an asymptote at negative 3 and at positive 3. And then we also have an inflection at 0. So this is inflection, and the other ones are asymptotes. Now, we said that we knew that our first derivative was always negative, which meant that we are decreasing everywhere. We don't even have to check it. Okay. But then, in order to find where so we've already done this part right here, because we knew that. We understood analytically what was going on when we saw our first derivative. And then we need to look at how our inflections are affecting things. So we're going to plug in test values here, 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 and here into our second derivative and see what happens. So right here, I'm going to say negative 100 can be our test. Here, negative 1 can be our test. Here, 1 can be our test. And here we'll do 100 as a test. Okay, so our second derivative is right here. Oh, I think I lost him. Nope. Okay, just so I can make sure I'm not plugging in something else. Okay, here we go. So I'm going to make this a little bit bigger. We have f prime prime of negative 100 equals, so we're going to have 2 times 100 times 100 squared plus 27 over 100, oh, this is supposed to be a negative 100, over negative 100 squared minus 9 cubed. Okay, well, 2 times negative 100, that's a negative. Negative 100 squared, that's going to be a positive, plus 27, so this is positive. Negative 100 squared is a positive minus a little bit cubed, that's still a positive. Well, since we have a negative times a positive, that's negative, divided by a positive, that's still negative. Or here, let's just do a minus. That's still negative. Therefore, we are concave down on the interval negative infinity to negative 3. So our concavity down looks like this, like we're frowning. Okay, now let's do the next interval test number. So we have f prime prime of negative 1 equals 2 times negative 1 times negative 1 squared plus 27 all over negative 1 squared minus 9 cubed. Okay, so here we have a negative, and then we have positive, but then on the bottom, this is going to be 1 minus 9, which is a negative. So we have here a positive, which means that we are concave up on the interval negative 1 to 0. And if you're like, hold on, how did that happen? Because we weren't at an inflection point. Well, we hit an asymptote. And things change because these are like complete breaks in our graph. So you always have to check what's going on around your asymptotes because, you know, things change. So there we go. We found that out. And then we have f prime prime of 1 equals 2 times 1 times 1 squared minus 9 all over 1 squared minus 9 cubed. Okay, so we see we're going to be positive. Why did I put that there? Y'all saw that? Okay, so my thing's taking a little while. Here we go. 1 squared plus 27. So we have a positive and a positive, but this is negative again. So we are negative, and we knew here, oh, I didn't draw it, that we were concave up. Here we know that we are concave down, and we knew that it was going to change here because we were at an inflection. So it doesn't always change at an asymptote, but you have to check because it can for our previous. So this is from 0 to 3, we are concave down. All right, and then for our next one, we have f prime prime of 100 equals 2 times 100 times 100 squared plus 27 divided by 100 squared minus 9 cubed. Okay, so this first part is going to be positive. Then we have another positive, and then 100 squared minus 9 is also positive. So this is positive, so we are concave up on the interval 3 to infinity. So if we look at these pieces here, we see at these. So we know that we have these asymptotes, right? And so they will go something like, we have an asymptote here, an asymptote here. And we know that we have an inflection point right there. So we know we have a point there. So if we see this right here, we know we're decreasing, 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 decreasing. Well, the only way before our asymptote at -3, which I'll make this a different color, these are our asymptotes. The only way for us to be decreasing concave down and simultaneously never touching our asymptote is going to be if we're in quadrant 3, because if we were concave down, we would eventually, you can't, it just wouldn't work right there. You'll have to do it right here, but you can also plot points, which we'll look at when we actually graph it. But I just want you to see what our graph is going to look like. So then I would take this bit right here, and this is from the -3 to -1 right here at our inflection. So we know that we have something going on right there at the inflection. So if we take this, it's going to be concave up, decreasing. But then we have this part, which is still decreasing, but now it's concave down, right? And then we have this on the other side of the other asymptote that is going, it's decreasing, but it's concave up. So the only way for that to happen is if it was like this. So you can get the whole character of your graph just by these lines. It's really cool. So let's go ahead and let's actually graph this. Okay, so it says graph f of x. Whoop. Let's do, all right, so the first thing we're going to do is graph, let's go ahead and make some marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's not at all the same. 1, 2, 3, 4, 5. And then here, do 1, 2, 3, 4. 1, 2, 3, 4. And then we'll go ahead and put in our vertical asymptotes. Remember, we never ever touch these. And then we also have a horizontal asymptote at y equals 0. So we want to make sure we take care of that too. And then we have an inflection point, remember, at 0, 0. So we want to go ahead and put that on here. So we have an inflection point at 0, 0. And then you can plot some points, which let's go ahead and do. So we'll, just to make sure we didn't mess something up. So we can say f of, let's plot some points on either side of this point that we know. So let's do -1 and 1 and just see what we get. So f of, come on, f of -1 equals -1 over -1 squared minus 9, which is going to give us -1 over 1 minus, that's -8, so 1/8. So we have a point at -1, 1/8. And then if we have, let's do f of +1, we'll get 1 over 1 squared minus 9 equals, equals 1 over -8. So that becomes -1/8. So we have a point at 1. Oh, I'm going to be right where my graph needs to be. 1, -1/8. Okay. So let's go ahead and plot those. So we have 1, -1/8. And then we have 1 at -1, +1/8. And then we can also plot some points on the other side of our asymptote. Actually, and we can even do these two if you don't yet see it yet. So we can say f of 2 equals 2 minus 2 squared minus 9, and that's going to give us 2 over 4 minus 9 is -5. So we have a point at 2, -2/5. So 1, 2, like that. And then f of -2 is going to give us -2 over -2 squared minus 9, which is going to give us -2 over -5, which gives us -2 positive 2/5. So we know that on the interval, this one is after the vertical asymptote, that we are decreasing concave up. So that's going to look, whoops, my points aren't the best here. It's decreasing concave up, and then we know right after that we are decreasing concave down right after this inflection point right there. So decreasing concave down. And then let's go ahead and plot some points. Let's plot just one. Over here we have -3. Just to see, make sure we didn't make a mistake. And so that's going to give us -3 over -3 squared is 9 minus 9. That gives us 0. -3 divided by 0 is undefined. Oh, because that is our vertical asymptote. So, which means our graph cannot touch there, right? So if we do -4, which is what I meant to do, then we're going to get -4. -4 squared minus 9. Well, that is going to equal -4 over 16 minus 9. 16 minus 9 is what, 7? -4/7. Yeah. So if we have -4, that's right here, we have a -4/7. So we know from our graph up here that we are decreasing concave down. So at least we know that we're in the right quadrant. We're in the third quadrant. And we know that we are decreasing concave down. Okay, well, what about the other side of our +3 asymptote right here? Well, let's go ahead and graph a point over here. So let's see what happens when we plug in a 4 into our function. If we say f of 4, we're going to get 4 divided by 16 minus 9. That's going to give us 4 over 7. So we have a 4 and a +4/7. So that means we're going to be in the first quadrant. This is 4 and then 4/7. And we know from doing our number line that we are still decreasing, but we're decreasing concave up. So how does that look? Like this. And there you go. You can see that we were able to see all of this just by doing the number line and putting them together. And the big thing here is to just practice, 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 and you'll start to see these things before you even really get through with the problem, especially once you get to the number line. Okay, let's do another one for practice. Okay, so we have a function, 3x squared divided by x squared plus 9. Well, the very first thing we want to find is our vertical asymptotes. And our vertical asymptotes are what will make our denominator equal 0, which therefore makes our function undefined. So these are domain restrictions that we're finding. So we set our bottom equal to 0, and we see, whoops, that it says x squared equals, and that'll say -9, which we know is going to be imaginary. So we have no vertical asymptotes. And you can also see, if you don't see it, that's fine. And you can do this. But if you see, this is +9. When we have a plus a little bit, that means that our bottom will never be 0, because even if x is 0, we still have a +9. So no matter what that is, we are never undefined. This is going to be continuous everywhere. All right, so now we need to find our horizontal asymptotes. And we do that by taking the limit as x goes to infinity of the top and the bottom, or just of the function. So we're going to have the limit as x goes to infinity. And remember, we are using, little thought bubble, we are using the fact that there's a theorem that says that if you have a constant over a power, or a variable, to any power, so this could be to 1, to 2, to 3, whatever it is, right? Then the limit is going to go to 0. So the limit as x goes to infinity of a constant over x to a power, or any variable to a power, is going to go to 0. And so we're going to make that happen here by dividing this, the highest power variable of the bottom, 1 over that for each part of our function, so that way we can utilize this. And what that looks like is we have the limit as x goes to infinity of the function, and then we're going to divide everything by x squared, because x squared is the highest power variable that we have in the bottom. And this equals, you have to keep writing this limit as x goes to infinity of, so you're going to get 3x squared over x squared. Then you're going to have x squared over x squared. Then you're going to have 9 over x squared. Well, what here in this matches this theorem? Well, this one does. This one's going to go to 0. So let's see then what we end up with. All right, so 3x squared over x squared is just going to be 3. X squared over x squared is 1. 9 over x squared is 0, because we're taking the limit of each bit. The laws of limit say that we can do that. We can take the limit of each part. So this is going to give us 3 over 1, which equals 3. This means that we have a horizontal asymptote at, let me just say at y equals 3. Now, our vertical asymptotes are areas that we can never ever touch, but our horizontal asymptotes, they let us know the behavior of our y's as our x gets infinitely large, like the tail ends of our graphs, and we'll see what that looks like. Okay, so our y-intercept is when x equals 0, so we're going to say f of 0 equals 3 times 0 squared, times 0 squared plus 9, which is 0 over 9, which is a defined 0. So we have a y-intercept at 0, 0. All right, now our first derivative. Our first derivative, here we go, we're going to have a quotient rule derivative, so that's going to be the bottom squared. Then we take the bottom as it is, times the derivative of the top, minus the top as it is, times the derivative of the bottom. And we'll put that all together, and we're going to get 6x cubed plus 6 times 9 is 54x minus 6x cubed over x squared plus 9 squared. Well, we see here that we can, those will go away, and we'll end up with that our f prime of x is equal to 54x over x squared plus 9 squared. Well, then we also need to find our critical numbers. And our critical numbers, remember, is when our first derivative equals 0. Well, the top will never make, or when it's undefined. So let me go back, because it is when it's also undefined. But this is never undefined, remember? Like we talked about before, it'll say, you'll see that your vertical asymptotes will come up here, but they're already going to be represented when we check them on our number line, so you don't need to put them. But the technical definition of your f prime of x is when your f prime of x is equal to 0, or when it's undefined, so when your bottom is equal to 0. However, that is not what we need for when we're sketching a graph. We just need to know when the numerator is equal to 0, because that is what is going to make our f prime of x equal to 0. Plus, remember we said this is continuous everywhere because this x squared plus a little bit, therefore the denominator will never be 0. Okay, so the top equals 0 when x equals 0. So we have a critical number at x equals 0. And our critical numbers are when we see a change in our direction. Now, f prime prime of x is our second derivative, and I'm going to move it up a little bit since we have some room. Okay. My pen has been getting where it doesn't want to switch. Okay. So we're going to do another quotient rule derivative. Well, we have x squared plus 9. Squared is to the fourth. But remember, just like in the beginning, we started off with a power of 1 and we ended up with a power of 2. Well, now we can only end up with a power of 3. So we know that one of these is going to cancel. So we want to keep our eye out for that. All right, and then we're going to say the bottom as it is times the derivative of the top minus the top as it is times the derivative of the bottom, so chain rule derivative, times the derivative of the inside. There we go. And then we will go ahead and put some things together here. So we see that we could take out a 54 and an x squared minus 9 from both of these. So let's do that. Okay, and then what do we have left? So we see that we have one of these left. That'll go in there. And then we come to our minus sign, and we see what we have left. Well, we need to put in a minus sign. And we took out 54, but we didn't take out an x, so we need to put that x there. And then we have a 4x, which we need to put right here. And that is already represented right there. All over x squared plus 9 to the fourth. Well, then that and that cancels. And we get 54. We have an x squared. This is going to be 4x squared minus 4x squared. That's going to leave us with a minus 3x squared plus 9 all over x squared plus 9 cubed. And then we see here that our second derivative is always going to be negative because we have this constant positive multiplier and a negative inside. So what does that mean? That means that this is always negative, and therefore we are always concave down throughout our whole graph. You can also take the negative out, and you would see that too. And then that would be, 3x squared minus 9. And you can actually simplify that a little bit more now that I'm looking at it. We could take a 54, and then we could take a negative 3 out of each. So then that would be x squared minus 3 all over x squared plus 9. Because remember, we want to simplify as much as possible. That'll make, when we're plugging things in for our derivative test for our number line, that'll make that easier to see what's positive or negative. Okay. So 54 times -3, what is that? That's 12, 15, 16, -162. X squared minus 3 over x squared plus 9 cubed. So this is our final derivative. Now our inflection numbers are what makes our second derivative equal 0. Well, this 162 will never be 0, but our x squared minus 3 could equal 0. So we have x squared minus 3 equals 0. Therefore, we have x equals plus and minus the square root of 3, which is like 1.7 something, right? We'll leave it, so we'll say approximately 1.7. I'm going to say plus and minus. All right, and then our critical points. Now remember, our critical points, they require for us to have a y value. So we had a critical number here at x equals 0. So let's plug x equals 0, whoops, into our original function. So we have f of 0 equals, and we know it's going to be 0. So we have a critical point at x, at 0, 0. Okay, and then I'm going to move this up a little bit. Okay, so our inflection points are where we have the square root of 3. So we're going to plug that into the original function to find our corresponding y value when x equals square root of 3. We have 3 times square root of 3 squared over square root of 3 squared plus 9. That's going to be just 3. This is going to be 3. And so we're going to have 9 over 9 plus 9, which is 18, which equals 1/2. Now when we have, so that means we have a point at square root of 3, 1/2. Or we have an inflection point, excuse me. And then we have, that's a negative, equals 3. And then we have minus square root of 3 squared, which is also just going to be a positive. And then we have negative square root of 3 squared plus 9. And this is going to be the same. It's going to be 3 times, this is just going to be 3. So that'll be 9 over 9 plus 9, which is 18, which equals 1/2, which is therefore going to equal negative square root of 3, 1/2. That will be our other inflection point. So where we are changing from concave up to concave down or vice versa. Okay, so now that we have these, let's draw a number line to show where f of x is increasing or decreasing, concave up or concave down. And I'm going to move this up. To give us a little bit more room. Okay, so let's say we have this number line, and we're going to put on here our critical numbers and our inflection numbers. Well, remember we had a critical number at x equals 0. So we have a critical at x equals 0, and then we have our inflection numbers right there. Okay, let's do this. And then we have inflection numbers at plus square root of 3 and minus square root of 3. All right, so here we go. Let's do critical at 0. And we'll do inflection at negative square root of 3, which is like negative 1.7. So that's negative square root of 3. And then over here is positive square root of 3, or positive 1.7. Oh. Okay, and then we need to pick test values in between here. So between 0 and 1.7, well, we have a 1. This is going to be a test value. Between here, we have a negative 1, which is going to be a test value. And then we can do negative 100 and positive 100. Okay, so we're going to plug all of these numbers into each derivative. The first derivative, though, is going to give us where we are increasing or decreasing, and our second derivative is going to tell us about the concavity on each of these intervals. So let's do this. So f prime of negative 100 equals, well, we have to have f prime, which is right here. And then our second derivative is right here. Okay. So we have everybody close by here for when we need them. Okay, there we go. So we have 54 times negative 100. So we know that's going to be a negative. And then we have, remember, we only care about the sign. And so then we have negative 100 squared, which is going to be positive. This is always going to be positive because it's squared. So we have a negative and a positive. Well, that's going to be negative. So therefore, we are decreasing from negative infinity to negative square root of 3. So we are decreasing. All right, now let's do our next one, negative 1. Well, it's going to be the same thing here. 54 times a negative 1 over something that's going to be positive. So we have negative over positive. That's going to be negative, which equals decreasing. So we didn't see a change in our decreasing or increasing here. From this to 0. And that's because we passed an inflection point. We change direction only at critical points and sometimes at vertical asymptotes. Okay, f of 0 is just going to be 0 over 9, which is positive. So therefore we are increasing from 0 to positive square root of 3. And then we have f of 100, which is going to be a positive over a positive, which equals a positive. And again, we didn't change direction here because we didn't pass a critical point. We passed an inflection, increasing from square root of 3 to infinity. Okay, now let's plug in our second derivative, our test values into that. So we have f of negative 100, and our second derivative was over here. So we have negative 162 times x squared, which is going to be negative 100 squared minus 3 over negative 100 squared minus 9 cubed. Okay, so we have 100 minus 9 on the bottom cubed. This is going to be a positive. The top is going to be a negative. So we have a negative, therefore we are, oops, not decreasing. We are concave down from negative infinity to negative square root of 3. Okay, let me give us some more room right here. Okay, now concave down, we'll do that in green. So that's our inflection. So we're concave down, decreasing concave down. And then we have f prime prime of -1. That's going to be -162 times -1 squared minus 3. Well, this is going to be a negative times a negative, which equals a positive, over -1 squared. And I just realized that I copied down, if you see this up here, this is why I need to make sure we have them bigger so I can see up here. This is a plus, x squared plus. See that? And I was making it a minus, so let me fix that. So we see this is supposed to be a plus. Whoops. So we have plus. Okay, so let's see if that changes our first one. So we have a negative times a positive, which is negative, and then this is still positive. So that doesn't change that, it's still concave down. Okay, so we have 1 squared plus 9 cubed. So we have a negative times a negative, which is a positive, divided by a positive equals positive, which equals concave up from negative square root of 3 to 0. Okay. And then we have f prime prime of positive 1, which is going to be -162 times 1 squared minus 3 over 1 squared plus 9 over 3. So then we have a negative times a negative, which equals a positive, over a positive again. So that's going to be concave up from 0 to positive square root of 3. And if you see here, we maintained our concavity. We did not change concavity. That's a bit of a mess, because we passed a critical point. Remember, we only changed direction at critical points, not concavity. All right. And then we're going to have f prime prime of 100. And this is going to be -162 over 100 squared minus 3 over 100 squared plus 9 cubed. So we have a negative times a positive, which is going to be negative, over a positive, which is going to be negative, and we just passed an inflection point, so we know that we are going to be, concave down from square root of 3 to infinity. Okay, so if we kind of look here, we can see that we have a decreasing concave down, we have an increasing, or excuse me, a decreasing. You'll see the change in concavity right about here, right? And so we start going up, and then we have up, 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 and then we're going to go back down again. You see that change in concavity? So we have this piece originally, and we have one piece, and then another piece, and then another piece. So let's see if that is how it ends up looking when we graph this. All right, so the next part of this is to actually graph it. So we can put everything together. So we're going to graph now. And we need to have all of our information together. So we know that we have critical points at, let's go ahead and gather our information here. We have critical points at 0, 0. And then we have inflection points at square root of 3, 1/2, and at negative square root of 3, 1/2. And then we also had a horizontal asymptote at y equals 3. And then we also have our y-intercept, which happens to be our critical point at 0, 0. Okay, so let's put all of this together and see what our graph looks like. Okay, so let's go ahead and put some lines on here. Okay, so we have a critical point at 0, 0. We have an inflection at square root 3, that's 1.7, 1/2, which that looks more like a 1. So I'm going to move my graph up a little bit because, as my teacher says, I'm the one with the pencil. And then negative square root of 3, which is negative 1.7, 1/2. And let's do our horizontal asymptote at y equals 3. So we have 1, 2, 3. Remember, you could cross this. It's not an absolutely don't touch. It's just showing us how our y is going to behave when our x values get really large. Okay, so then if we put everything together, now we could graph some more points, because where is our actual function? If you wanted to do that, you could graph some more points. Let's bring them on down. Okay, so he's going to have to be made a little bit bigger. We're going to just put f of x is 3x squared over x squared plus 9, so we can actually see him here. Okay, so let's graph some points. Let's do f of, let's see, that's 1, 2. Let's do f of 3, and that's going to be 3 times 3 squared times 3 squared plus 9. Well, that is 9. That's 27 over 9 plus 9, which is 18, which is going to give us what? What is that actually equal to? 27 divided by 18 is 1.5. So we have a point at 3, 1.5. So we have 1, 2, 3, and then a 1.5. All right, and then let's do the same for the other side. F of negative 3, which is going to be 3 times negative 3 squared times negative 3 squared. When these are squared, it's going to end up being the exact same thing, right? So we have 1.5 again, but now it's going to be, oh goodness, you realize I just actually mapped that one. This one was supposed to be over here because it's positive 3. Okay, 1, 2, 3, and then 1.5. Oops, that's in purple. We want you in red. 1.5. And then we're going to do the same thing over here. We have 3. So we are seeing that our graph is really symmetrical, right? Well, let's do a little bit further out. And let's say 1, 2, 3, 4, 5, 6. Let's say f of 6. 3 times 6 squared divided by 6 squared plus 9 equals, so we have 3 times 36, it's going to be 108, divided by 36 plus 9, so 36 plus 9 is 45. And then we have 108 divided by 45. That's going to give us 2.4. So we have f of 6. So that's 1, 2, 3, 4, 5, 6. And we're going to go up 1, 2, 3, to 2.4. And we know now that it's going to be the exact same thing because it's got that squared. So it'll be just the opposite for, and I did it again, y'all. I did it again. This is positive 6. My x is positive. So this is my point. 6, 2.4. So I need to put that on the positive side. 1, 2, 3, 4, 5, 6. 2.4. So you'll see that we're getting really, really close to this horizontal asymptote, right? And then we have 2.4. So that's going to be the same over here. 1, 2, 3, 4, 5, 6. And then 2.4. Okay. So now let's put together everything that we had. So we knew if we bring these down here, had some crazy stuff that came with it. We'll see that we are decreasing from negative infinity to this 1.7 mark. So we are decreasing, let's see, that's at square root of 3, we said was right here. Whoops. Come on, pencil. Work with me, work with me. Okay, square root of 3, negative square root of 3 was right there, and positive square root of 3 was right there. So we know that we are decreasing concave down until we get right there. Okay, so then we change concavity and we start to increase until, well, we're still decreasing, but we start to change our concavity at square root of 3. And then we have the same concavity right here, you'll see, from 0 to the next square root of 3, we're still concave up. But now we're increasing. And then we're going to have another inflection point at the square root of 3. And so that means we're changing our concavity. We're still increasing, but now we're increasing concave down. And that's going to go on for infinity. Okay. And that is how you do these. And so I think the big thing with these is to just practice, practice, and let yourself, don't be afraid to mess up. Messing up is part of the process, right? And just have fun with it. And remember that you can learn anything. You can learn absolutely anything. All right. Hope this was helpful.